Team, next topic we're going to be covering today is upper and lower bounds. This is usually considered like a grade topic, but I think it's actually pretty straightforward once you get a technique down. So let's first look at the definition of what an upper and lower bound is. Upper and lower bounds are the upper and lower values that a number can have as a result of rounding or approximating that number. Let's try and explain this in terms of an example. Let's say we're at a stadium. All right, it's a big stadium, and you're standing here, and someone calls you up, and they're like, "Yo, how many people are at the stadium?" When someone asks you this, are you going to count every single person in the stadium to find out how many people there are? Probably not. You're going to guess. So what you can say is, "Oh, there are 50,000 people." And then, so you can say there are approximately 50,000 people, but you have to give your limit of accuracy. Is it 50,000 to the nearest 100 people, to the nearest 1,000 people, to the nearest 50 people? So perhaps you say there are 50,000 people approximately to the nearest 1,000, to the nearest 1,000. And what we do with upper and lower bounds is find out what's the upper limit to your estimates and what's the lower limit to your estimates. Let's look at the upper bound and lower bound for this example. So you said there are 50,000 people at the stadium to the nearest 1,000. So we got to find the greatest number of people possible in the stadium. That's called the upper bound. What we do is we can draw a little straight line, and in the middle we're going to write down our approximation. We're saying it's 50,000 people. And then a lot of people say, okay, if there's 50,000 people to the nearest 1,000, the upper bound is going to be 51,000. And the lower bound will be 1,000 less than 50,000, so 49,000. But if you were to think of the number, if you were to say there's 49,000 people at the stadium, 49,000 to the nearest 1,000 is 49,000, not 50,000, which is what we want. So how do we find the upper and lower bounds? Step one is, actually we're going to do what we just did. We're going to add 1,000 and subtract 1,000 from our approximation. So 50,000 plus 1,000 is 51,000. And 50,000 minus 1,000 is 49,000. Now, our upper bound is going to be the midpoint between our estimates and this number here. So middle of 50,000 and 51,000 is going to be 50,500. And that'll be our upper bound. And our lower bound is going to be the other side. The midpoint between 49,000 and 50,000, which is going to be 49,500. Because if we round 49,500 to the nearest 1,000, it'll go to 50,000. If we do anything less than 49,500, it'll round down to 49,000. So we can say the least possible people is 49,500. The number of people must be more than or equal to 49,000. And 50,500 is our upper bound. 50,500, if we round it to the nearest 1,000, it'll actually be 51,000. So it has to be anything less than this number. So our upper bound is going to be, so our number of people must be less than 50,500. Because if I choose any number less than 50,500, like 50,499, it'll round back down to 50,000, which is what we want. So our upper bound in this problem would be, upper bound is 50,500, and our lower bound is going to be 49,500. So let's look at some upper bounds and lower bounds for some other questions. Let's rub this all out first. The length of a table is 105 centimeters to the nearest centimeter. Work out the smallest possible length of the table. If we're being asked for the smallest possible length of the table, we're looking for the lower bound. So we know a table is approximately 105 centimeters. So we'll draw our number line. It's approximately 105 centimeters. And that's our degree of accuracy is to the nearest centimeter, aka the nearest 1 centimeter. So we're going to add and subtract 1 centimeter from both sides, 106 centimeters and 104 centimeters. And to find the smallest possible length of the table, we're going to find the midpoint of 104, 105. So lower bound, the midpoint of 104 and 105 is going to be 104.5. And that's the lower bound. That's the smallest possible length the table can be, 104.5 centimeters. Now, the upper bound. Write down the largest possible length of the table. Well, the upper bound is the midpoint between 105 and 106, which is going to be 105.5. Our table, the most it can be is 105.5 centimeters. Let's look at the next question. So actually, before we go to the next question, I just want to elaborate on something. A lot of people get confused with the upper bound because 105.5 to the nearest 1 centimeter is 106 centimeters. But still, for the sake of this topic, we'll still say the largest possible length is 105.5 centimeters. Let's look at the next question. The speed of a car is 50 miles per hour, correct to the nearest 10 miles per hour. So we're guessing the speed of the car is 50 miles per hour. And we're asked to find the lowest and greatest possible speed. Well, what we're going to do is we can see that 50 miles per hour is correct to the nearest 10 miles per hour. So we're going to add and subtract 10 miles per hour on both sides. 50 plus 10 is 60 miles per hour. And 50 minus 10 is 40 miles per hour. To find the lowest possible speed, it's the midpoint of the here. So the lower bound will be, midpoint of 40 and 50 will be 45. So that's the lowest possible speed, 45 miles per hour. The greatest possible speed is the midpoint between 50 and 60, which is going to be the upper bound, and that's going to be 55 miles per hour. And that's it. Let's look at the next page. The distance between the Sun and Earth is 150 million kilometers, correct to 2 significant figures. Write down the lower bound. All right, let's draw our number line. So we're guessing the distance between the Sun and the Earth is 150 million kilometers. We don't know the exact distance, but we're guessing it's about 150 million kilometers. And we're guessing to the nearest 2 significant figures. Well, whenever we're trying to find the lower and upper bound using significant figures, let's look at this number first of all, 150 million to 2 significant figures. Well, this is the first significant figure. This is the second significant figure. So let's look at the second significant figure. And this place value is the 10 millions column. Because units, 10, 100, thousands, 10,000s, 100,000s, millions, 10 millions. So basically, the second significant figure is the 10 million column. So we're correct to the nearest 10 million. So we're going to add 10 millions to both one side, so 160 million, and subtract 10 million from the other side, 140 million. The lower bound is the gap between these two numbers, lower bound. Well, the middle of 140 million and 150 million is 145 million. So that's our answer for the lower bound. And then the upper bound is the gap between these two numbers, upper bound. The midpoint of 150 million and 160 million is 155 million. Let's look at question 3. We'll do this on the next page, actually. Write down the upper and lower bound for each of the following. So we'll just do these ones quite quickly. So 3.8 centimeters to the nearest 1 centimeter. So, 0.1 centimeters. So 3.8 centimeters. It's being rounded to the nearest 0.1 centimeters. So we're going to add 0.1 centimeters to both sides. So 3.8 plus 0.1 is 3.9. And 3.7 if we subtract. So a lower bound is this over here, which is 3.75. So the lower bound is 3.75, and the upper bound is 3.8, 3.9, 3.85. And that's the upper bound. Let's do the next one. 15.2 seconds to the nearest tenth of a second. 15.2. It's rounded to the nearest tenth of a second. So here, a tenth is basically 0.1. So we're going to, that's in seconds. So we're going to add 0.1 to both sides. 15.3, 15.1. The upper bound, the lower bound is this, is a space here. The middle of 15.1 and 15.2 is going to be 15.15. So that's the lower bound. And this gap between 15.2 and 15.3 is 15.25, which is upper bound. And then final one, 6.4 grams rounded to 1 decimal place. So 6.4 grams to 1 decimal place. So 1 decimal place means the first decimal place. The first decimal place is always a tenth. So we're going to add and subtract 1/10, which is basically 0.1 to both sides. So 6.5 and minus 0.1, 6.3. The midpoint is going to be 6.35 grams. What the heck was that? Which is the lower bound. And the upper bound will be the midpoint between 6.4 and 6.5 grams, which is 6.45 grams. All right, on the next page, I'm going to give you some work you can try. Some few questions on upper and lower bounds, just finding the bounds. The first question is a past paper question. This section here is measuring to the nearest gram, mile, seconds, and kilometers. This part here is about rounding with significant figures, and this part here is about rounding with decimal places and whatnot. Give some of these a try and let me know if you have any problems. Thanks. Let's try some word problems together. Let's look at the first one. Y equals 1.8, correct to 1 decimal place. Calculate the lower bound for the value of 4y plus 1. So we want to find the lower bound for this expression, 4y plus 1. If we're trying to find the lower bound, we're trying to find the smallest possible value, the lowest possible value. So if I'm trying to find the smallest possible value for this expression, I first have to replace this y value with a number. And we have to just figure out, should I replace y with 1.8? Or should I replace it with its upper bound or its lower bound, which we'll find? Well, let's first find the upper and lower bound of value y. So y is 1.8. We'll draw our number line. And it's correct to 1 decimal place. So 1 decimal place means the first decimal place. The first decimal place is called a tenth. So we're going to add 1/10 to the beginning and the end. So 1/10 will be 1.9 and subtract tenths will be 1.7. Then the upper bound will be the gap in the middle of 1.8 and 1.9, which will be 1.85. And the lower bound will be the gap between 1.7 and 1.8, which will be 1.75. Which will be the lower bound. So in order to find the smallest possible value of 4y plus 1, should I replace y with 1.75 or 1.85? Well, when we're multiplying, to get the smallest possible answer, y must be as small as possible. All right? So what we're going to do is we're going to replace y with the lower bound. So what we're going to do is we're going to do 4 times 1.75 plus 1. And let's get my calculator out. Oh. Where's that? One sec. That will be 4 times 1.7, 1.75 plus 1 is 8. So this is the lower bound of 4y plus 1. Because if I was to replace y with 1.85, that would be a bigger answer. That would be 8.4. But we want the lower bound, so the smallest possible value, hence that's going to be 8. And that would be our answer. Let's look at the next problem. V is equal to S divided by T. S is 4.15, correct to 2 decimal places. T is 2.516 to correct to 3 decimal places. And work out the upper value for V. Give your answer to 3 decimal places. So we want to find the upper value for V. That means the largest possible value. Okay, now let's think about division. When we're dividing, how can we get this largest possible answer? Well, when I do these kinds of questions, I like to make up an example. Let's say I'm doing A divided by B. Okay, and I want to get in this case, I want to get the largest possible answer. What I do is I choose 2 values for A. It can be anything you want. We'll make one really big and one really small. And we'll do the same thing for B. One really big, let's say 10, and one really small, 2. And I want to think, how can I make the largest possible answer? Well, in order to do so, I need a really big first number and a really small second number, because 100 divided by 2 will give me 50, and that's the largest possible answer you can get, either choosing these 2 numbers or these 2 numbers. So basically, when we're dividing, if we want to get the largest possible value, the numerator or the dividend must be the highest possible value. So we have to find the upper bound for S. So we need to find the upper bound for S. And then for the divisor, the second number, we want to get the smallest possible value. So for the value T, we want to find the lower bound. And that should give us the upper bound for V. So we have to find the upper bound for value S. Well, S is 4.15. To correct to 2 decimal places, so 1, 2. This place value is called a hundredth, so I'm going to add and subtract a hundredth to both sides, so 4.16 and 4.14, and we want to find the upper bound for S, which is this over here, and that will be 4.155. So our value for S will be 4.155, and for T, the divisor, we need to find the lower bound. So let's get our our number. For T, 2.516. It's correct to 3 decimal places. So 1, 2, 3. This is a third decimal place. This is called a thousandth. So I'm going to add and subtract a thousandth to both sides. 517. 515, and I want to find the lower bound. So that's going to be 2.5155. So T will be 2.5155. And that should give us the largest possible value for V. 4.155 divided by 2.5155. And that's our answer, 6.652. So when we're dividing, if we want to get the largest possible answer, the top number, the numerator, the dividend must be the upper bound. We're dividing lots of sweets by the very few people. The divisor has to be very small. Let's look at the next problem. The final velocity of a traveling object is given by the formula v equals u plus at, where v is the final velocity, u is initial velocity, a is acceleration, and t is the time. Given u is 2.4 meters per second to 2 sf, a is 12 meters per second squared to 2 sf, and t equals 5 seconds squared to 1 sf, calculate the lower bound for v. So we want to find the lower bound for v. So that's the lowest possible value for v. Well, first of all, u is being added by at. When we're adding and we want to find the lowest possible value, we have to add two small numbers. 1 plus 1 will give us a far smaller number than 100 plus 100. So first things first, u, we have to find the lower bound, and at, we have to find the lower bound. So let's start with u. We have to find the lower bound for u. So u is 2.4 to two significant figures. So the first significant figure, the second significant figure. The second significant figure is a tenth. So we're going to add a tenth to both sides. So 2.5, 2.3. And we got to find the lower bound. So here, 2.35. So our value for u is going to be 2.35. And now, a times t, we have to find the lower bound, or the lowest possible value. When we're multiplying, and we want to find the lowest possible value, our two numbers must be as low as possible. 2 times 2 is going to be far lower than 100 times 100. So we got to find the lower bound for a and the lower bound for t. So let's find the lower bound for a. 12 to two significant figures, so 1, 2. The second significant figure is a unit. So we're going to add 1 unit, or just a 1, 11. And we're going to find the lower bound, which is going to be 11.5. So our value for a will be 11.5. And then we're going to find the lower bound for t. Well, t is 5 to one significant figure. 5 is a unit, so we're going to add a 1 to both sides. And we're going to find the lower bound, which is going to be 4.5. So t is 4.5. So these are our numbers we're going to use to find v. So v equals u, which is 2.35, plus at, 11.5 times by t, which is going to be 4.5. And that should be the smallest possible value, aka the lower bound for v. Plus 54.1. And that's our answer. Here are some questions you can try in your own time. And let me just give you a little summary about calculations when it comes to bounds. So when we're adding values, imagine we're adding a plus b, and we want to find the upper bound, the largest possible answer. When we're adding, to find the largest possible answer, we want to add two large numbers, upper bound plus upper bound. If we're adding and we want to make the smallest possible answer, so a plus b, and we want to find the lowest possible answer, the lower bound, we'll get the lower bound for a and the lower bound for b. How about when we're subtracting? We're doing a minus b, and we're trying to find the upper bound. So we're doing a minus b, and we're trying to find the largest possible answer. Let's do that same exercise as before. Let's choose two numbers for a, 110, and two numbers for b, 5 and 1. So we have a choice of choosing 100 or 10 for a, and 5 or 1 for b. And we want to get the largest possible answer. Well, it has to be 100 minus 1 will give us 99. That's probably the largest answer you can get. So we have to find the upper bound for a and the lower number for b, or the lower bound for b. And then it's going to be the opposite. When we're subtracting a minus b, and we want to get the lower bound, we have to get a really small first number, 10, minus a big second number. So it'll be lower bound minus upper bound. When we're multiplying, it's the same as adding, really. A times B. We want to find the upper bound. If we're trying to find the largest possible value, A has to be really big, B has to be really big. And conversely, if we're trying to find the smallest possible value, A has to be really small, B has to be really small. And then division is like subtracting. We're doing A divided by B. We're trying to find the upper bound. We want to have the most number of sweets divided by the least number of people. So each person has a lot of sweets. And on the flip side, if we're doing A divided by B and we're trying to find the lower bound, we're trying to find the lowest number of sweets per person. There has to be very few sweets shared between as many people as possible. So lower bound divided by upper bound. Which is just a little cheat sheet you can use when it comes to bounds. But instead of trying to memorize it, just try and understand what's going on, okay? And yeah, try these questions over here. Okay, let's do some bounds, some word problems. ABCD is a rectangle. The perimeter of ABCD is 64 centimeters. Correct to the nearest centimeter. AB is 17 centimeters. Correct to the nearest centimeter. Calculate the lower bound of the length AD. Show your work clearly. All right, a lot of information here. Let's just go step by step, line by line. ABCD is a rectangle. All right, let's draw a rectangle out. Yep. And so A, we'll not label it yet. The perimeter is 64 to the nearest centimeter. So to the nearest 1 centimeter. AB is 17, so I'll say AB is 17, and CD. And AB is 17 to the nearest centimeter. So 17 to the nearest 1 centimeter. Calculate the lower bound of this length here. All right, so I want to find the lower bound of A to D, of the length AD. That means I want to find the lowest possible length. If I want to find the lowest possible length, let's first think about the perimeter of this rectangle. If A to D must be as small as possible, do we want our perimeter to be really big or really small? Well, we want it to be a really, really small perimeter, because the smaller the perimeter, the smaller the side lengths will be. So we're going to find first the lower bound of the perimeter. So we'll use our number line, 64. It's to 64 to the nearest centimeter, to the nearest 1 centimeter basically. So 65 centimeters, 63 centimeters, and we're going to find the lower bound. So we're going to use the lower bound of the perimeter. So we're going to say all the side lengths are going to add up to 63.5 centimeters. Next, so we know all the sides must add up to 63.5. Now let's look at A to B. Well, we know A to B is approximately 7 centimeters to the nearest 1 centimeter. Do we want to find the upper bound or lower bound to make sure A to D is as short as possible? Well, the longer that the length is, the shorter that the width will be. On vice versa, if the length is short, the width will be really long. Since we want the lower bound of the width, we want to have a really short width. We're going to find the upper bound of the length, okay? So we're going to find the upper bound of A to B. So we're going to draw our line. This will be 17, and it's 17 to the nearest centimeter, to the nearest 1 centimeter. So we'll add 1, 18 centimeters, and subtract 1, 16 centimeters. And we want to find the upper bound. So we're going to say the length of the rectangle is going to be 17.5 centimeters. So We know A to B and D to C are 17.5. We know the perimeter is 16.5, and we're trying to find the length of A to D. So how do we find the perimeter? Well, we just add up all the side lengths. We have to add this side, plus this side, plus this side, plus this side. So it'll be 17.5 plus this side, we'll call it X, plus this side, 17.5, plus this side. Well, this side, BC, is the same length as AD. So this is X, this will also be X, plus X, and that should be 63.5. We'll combine 17.5 and 17.5. That will be 35. X plus X is 2X equals 63.5. We'll now just solve the equation. We'll minus 63 on both, minus 35 on both sides. So that cancels out. It'll be 2X is equal to 63.5 minus 35. Going to be 28.5. And we're going to divide by 2. So X is 14.25. So that's going to be the lower bound of the length, A to D centimeters. Let's move on. A car travels a distance of 63.5 kilometers correct to the nearest 0.5 kilometers. The car takes 45.8 minutes correct to 1 decimal place. Work out the lower bound for the average speed of the car. Show you're working clearly and give your answers in kilometers per hour correct to 1 decimal place. All right, so let's draw a picture of this problem. A car travels a distance of 63.5 kilometers to the nearest 0.5 kilometers. Let's draw a picture of a road. And this road is 63.5 kilometers, approximately, to 0.5 kilometers. Then we know the speed of the car. The time taken would be 45.8 minutes, approximately, to 1 decimal place. And we're trying to find the speed. So we're trying to find the speed. We have the distance and time. If we're trying to find the speed and we have the distance and time, there's actually a formula we can use. The formula we're going to use is speed equals distance over time. Okay? Now, we're trying to find the lower bound for the speed. Okay? So that's the lowest possible value. Lower bound means lowest value. So over here, if we're trying to find the speed, we have to do distance divided by time. If we go back earlier to thinking about our bounds, if we're trying to find the lowest possible answer in a division problem, what do we need? Well, you can go back to that cheat sheet. If we're trying to find the lowest possible answer for a division problem, we need a lower bound for the numerator, or the top number, and the upper bound for the denominator, okay? So we need to find the lower bound for the distance. So our distance is 63.5 kilometers to the nearest 0.5 kilometers. So we're going to add 0.5 kilometers, which will be 64 kilometers, and subtract 63.5 kilometers by 0.5 kilometers, which is 63 kilometers. And we're trying to find the lower bound. So our lower bound is 63 point. The middle of 63 and 63.5 is 63.25, and that's going to be the lower bound of the distance. So the speed, find lower bound, we're going to use 63.25 kilometers as our distance. And we're going to find the upper bound for the time taken. So 45.8 to 1 decimal place. So we're going to find the first decimal place, and that place value is called a tenth. So we're going to add 1/10 and subtract 1/10. And we're going to find the upper bound. So it'll be 45.85. And that's going to be the time taken, 45.85 minutes. So now we can divide those to find the lower bound. 63.25 divided by 45.85. That gives us a speed of 1.379 kilometers per minute. But we want to give our answer in kilometers per hour. So if we travel 1.379 kilometers in 1 minute, per minute means per 1 minute, we have to find out how far we travel per 1 hour, which is 60 minutes. So what we have to do is multiply our answer by 60, because 1 hour is 60 times bigger than 1 minute. So times 60. And it'll give us an answer of 82 correct to one decimal place, 82.8 kilometers per hour. So what I did was I realized we have to use our speed, distance, time formula. It's a division problem, and if we're trying to find the lower bounds in a division problem, we do the lower bound of the first number and the upper bound of the second number, and that'll give us the lowest possible answer. So I found the lower bound of the distance, which was 63.25, then the upper bound of the time taken, which is 45.85. We divided it, and that gives us the kilometers per 1 minute. So to find the kilometers per hour, we just multiply by 60, because there's 60 minutes in 1 hour. All right, gang, last question. A metal cube has side lengths of 4.5 centimeters, correct to 0.5 centimeters. The cube is melted down and the metal is used to make small spheres. Each sphere has a radius of 3 millimeters, correct to the nearest millimeter. Work out the greatest number of spheres that can be made from the metal. Show your working clearly. So we have a metal cube which has sides of length 4.5 centimeters. Let's draw a cube out. Is there a cube we can find here? No, it doesn't look like it. Here, let's draw this. So we have a cube. And it's got sides of length 4.5 centimeters. So this is 4.5 centimeters. This is 4.5 centimeters. This is 4.5 centimeters. And all of these numbers are approximates. It's 4.5 centimeters to the nearest 0.5 centimeters. And this cube is melted and used to make small spheres. So what's going to happen is we're going to melt this cube and we're going to use it to make these tiny spheres which have a radius of 3 millimeters approximately to the nearest millimeter. And we want to find out the greatest number of spheres that can be made from the metal. Before we start thinking about the lowers and upper bounds of this problem, let's think about how this would work. We have this big cube. We have to melt it, okay? And when we melt it, we're going to use it to make these small spheres. Therefore, we have to find out the volume of the cube, because the volume is basically the amount of metal inside the cube. And we're going to use that volume of metal to create small cubes. I mean, to create small spheres. So we have to find first the volume of the cube, because that tells us how much metal is it made out of. And with that metal, we'll make the spheres. Now, if we want to find the most number of spheres possible, we want to have a really big cube. Because the bigger the cube, the greater the volume of the cube. The more metal that we can melt, and the more spheres that we can make. Now, when it comes to the spheres, we have to find a volume as well, because the volume tells us how much metal the sphere is made out of. If we're trying to make as many spheres as possible, we want to have a really small sphere, because the smaller the spheres, the more we can make. So first, we have to find the upper bound for the volume of the cube, and the lower bound for the volume of the sphere. If we want to find the volume of a cube, we have to do length times width times height, okay? But we know all these numbers are approximations. They're approximations to the nearest 0.5 centimeters. If I want to find the biggest volume possible, I want to find the upper bound for all these sides. Let's go ahead and find the upper bound for 4.5. So 4.5 to the nearest 0.5 centimeters. So I'm going to add 0.5 to both sides. and I'm going to find the upper bound. So I want the longest sides possible, which will be 4.75. So we're going to say all the sides of this cube have lengths of 4.5 centimeters, 4.75 centimeters, and 4.75 centimeters. And we can take off all this other stuff. And now we can find the volume of this cube. To find the volume, it's just going to be 4.75 times 4.75 times 4.75. And our volume of our cube will be 107.171875 cm cubed. Okay? Now we want to find the lower bound of the volume. The first thing I notice is that this is in millimeters. If this is in centimeters, and this is in millimeters, it's going to make our question really difficult. So why don't we turn the millimeters into centimeters? 3 millimeters is actually 0.3 centimeters. We just divide it by 10. So there's 10 millimeters in 1 centimeter. And now we have to find the volume of the sphere. Well, if I want to find the smallest possible volume, we want the radius to be as small as possible. Smaller the radius, the smaller the volume. So we're going to find the lower bound of the sphere radius. So it's going to be 0.3 centimeters to the nearest millimeter. Okay? A millimeter is also known as 0.1 centimeters. So we're going to add and subtract 0.1 centimeters to both sides. And we're going to find the lower bound, 0.25 centimeters. So we're going to say the radius of our sphere is 0.25 centimeters. And now we can find the volume. If you look at your formula sheet, the volume of our sphere is 4/3 pi r cubed. So we can do 4/3 pi 0.25 cubed. So times pi times 0.25 cubed. And each sphere has a volume of 0.06544 centimeters cubed. So we know the volume of the cube has a volume of 107, and the volume of a sphere is 0.06 centimeters cubed. How many 0.06s can be made from 107? We can just divide them. (107.171875) divided by 0.06544. We can make 1,637.71 spheres. Obviously, you can't make 0.71 of a sphere, so we can only actually make 1,637 spheres. And that is our final answer. So what we did was I realized that in order to make the spheres, I have to find the volume of the cube. And since I want to make as many spheres as possible, I want a really big cube. So I found the upper bound of all the lengths and then found the volume. And since I wanted to make as many spheres as possible, I wanted the spheres to be really small. So I found the lower bound for the radius of the sphere and to find the lowest possible volume. So if I know the volume of a sphere is 0.06 centimeters cubed, and the volume of the cube is 107, we can do 107 divided by 0.06 to see how many spheres can fit inside the cube. And over here is some questions you can try by yourself. Give it a pause and let me know how you do, and I'll answer any questions that you have. Thanks.